Welcome back, Physical Science 20. This is the PW3 section, so the very first one, and looking at refraction of light. So last time we looked at reflection, that was the whole last unit. This is the new one dealing with refraction, and in particular, refraction of light is what we're going to be concentrating on here. So we'll look at what is meant by refraction, examine the behavior of waves undergoing refraction by applying Snell's Law, which looks like this, and we'll look at that. To solve problems related to the refraction of waves, relate refraction and the refractive index of a medium to the change in speed and direction of waves at a boundary between different media, and explain the behavior of waves when something referred to as the critical angle is reached, and that results in TIR, total internal reflection. So we'll start with an example, and one that you're likely familiar with, and that is of a swimming pool. Looking at the surface of a swimming pool on a summer day, you can see sunlight reflecting off the water. You can see objects that are in the pool, because some of the light travels into the water, reflects off the objects, and comes back out and enters your eyeball. When you look closely at objects in the water, however, you'll notice that they often look distorted. For example, things beneath the surface look closer than normal. The feet of a person standing still in the pool may appear to be moving back and forth, and lines along the bottom of the pool seem to be swaying back and forth as well. These effects occur because light changes directions as it passes from water into air. So that's getting into refraction. The path of a light is bent as it crosses the boundary between two different media due to refraction. So that is the bending of light as it exits one medium and enters another. As seen in the figure above over here, it's kind of difficult to see, but what this is just a glass block, pencil, and you can see that the pencil is here, but it appears to be shifted here, because inside there, light inside that piece of glass exiting into air refracts or bends, so it appears if we extend the lines backwards, it appears that it has moved. So the bending of light makes objects appear to be shifted from their actual locations. The amount of refraction depends upon the properties of the two media, how optically dense they are, and the angle at which light strikes the boundary. As waves travel along the surface of the water, the boundary between the air and the water moves up and down and tilts back and forth. The path of light leaving the water shifts so the boundary moves, causing objects under the surface to appear to wave or shake. So that leads into something referred to as Snell's Law of Refraction. What happens when you shine a narrow beam of light at the surface of a piece of glass, like over here? As you can see, it appears to get bent. Well, it doesn't appear, it does get bent. It bends as it crosses the boundary from air to glass, and look, when it goes back from glass into air, it bends again. The bending of light, called refraction, was first studied by René Descartes and Willebrord Snell about the time of Kepler and Galileo. To discuss the results of Descartes and Snell, you have to define two angles. We have the angle of incidence, which is this one right here. So the incoming angle, and it is the angle. So if I draw a normal line, and by normal it's this dotted line, and it is actually 90 degrees. The word normal forms a 90-degree angle with the surface, so it forms 90. So we define the angle I as being the angle between that normal line and the angle of the ray coming in. Okay? So we have the angle of incidence, which is the angle at which light strikes the surface. It is measured from the normal to that should be actually the light beam. So the normal to the surface, normal to where that angle is, where that light ray is. The angle of refraction is the angle at which the transmitted light leaves the surface. It is also measured with respect to the normal. So normal and light ray. Normal and light ray. And as you can see, when we're going from air to glass is considered more optically dense. The beam goes towards a normal. So you can see that angle 2, or angle R, refraction, is smaller. it also is measured with respect to the normal. In 1629, Snell found that when light passed from air into some substance which is denser than air but still transparent, this is how the signs are related. The sine of the angle 1 over sine of angle 2 gives us an n. And of course, if we look here, big angle, small angle, we will get a value bigger than 1 over here. N is a constant, and it depends upon the substance, of course. We're going from light into what substance? Not on the angles, and it's called the index of refraction, or the refractive index. The indices of refraction for some substances are listed here. We take a standard type of light here, yellow light, and of course going from a vacuum into a vacuum is 1. Going from air into air is 1. Very close, a little bit bigger. For all intent and purpose, we can say it's 1. Going from air to water, we get 1.3. So you can see the greater the n value here tells us how optically dense it is. Look at diamond, 2.42. That's the biggest index of refraction. So a lot of bending there, and that leads into something interesting coming up. So we could also relate this in terms of Snell's law of refraction. It's basically the same thing here, because if I was to multiply this, sine theta 1 is equal to n sine theta 2. And of course, this n really is the index of refraction in the other medium. And it just so happens here that n1, if we're talking about air, notice that it's equal to 1. From this table down here, it's equal to 1. So of course, that n basically is 1, so we don't need to include it. So that's why we sometimes write it like that. So looking for n2, theta, sine of theta 1 divided by sine theta 2. So it's derived from this relationship. Looking again at the figure on the top right of this page. So if you look, and we could apply that law for each part here. You can see how Snell's law applies when light travels through a piece of glass with parallel surfaces, such as a window pane. The light is refracted both when it enters the glass and then again when it leaves the glass over here. And notice, interesting thing here, these two lines here are parallel, but it's shifted over. Lateral inversion. So if I had my eyeball here, if I had an object over here, it would appear, because my eyes would think, oh, let's extend this line backwards to see where it is. Oh, it's shifted over here. So things appeared to be shifted over. So that's relatively interesting. When light goes from air to glass, it moves from the material with lower index to the one with the higher index of refraction. So that is my initial substance, which in this case was air, is less than n2. To keep both sides of the equation equal, we must have sine theta equal bigger than sine theta 2. So if I was looking this, if I know that n2 is bigger than n1, to keep this equal, increase this, decrease this. So to keep it equal. And of course, vice versa, when light travels from glass to air, it moves from material having higher index of refraction to one of lower. N1 is bigger than N2, so that corresponds to a smaller sine theta 1 compared to sine theta 2. So note that direction of the ray when it leaves the glass is the same as it was when it struck the glass, but it's shifted, as I mentioned. So again, so it appears that, things have been shifted because these two exit lines are parallel. All right, let's take a look at an example. So we'll look at, I'll use the longer form of Snell's law. So a light beam in air hits a sheet of crown glass at an angle of 30 degrees. What's the angle of refraction? So we can imagine it like this. So here we have air. What is this? This is crown glass. So I can write crown glass here. Here's my normal. And we're told that this beam of light is coming in at 30 degrees. So of course, now from what we saw on the previous page, the angle of refraction should get smaller. So that's what we're looking for there. So substance 1 is air, and for our intent and purpose, we can just simply say it's 1.00. N2, if we look that up, and of course you'll have access to this table, crown glass, 1.52. And theta 1, we're told is 30. and theta 2 is what we're looking for. So we can set that up. N1 sine, let's just do that over. N1 sine theta 1 equals N2 sine theta 2. So enter everything in here, 1.00 multiplied by the sine of 30 is equal to N2 multiplied, and N2 we know, right? It's a crown glass, which is 1.52. Ooh, that's messy, messy, messy. I'll use some magic to fix that up. So magic, there you go, it's all fixed, 1.52. And we're looking for theta 2, obviously. So super easy, super easy. So we divide by 1.52, divide by 1.52. So we'll have sine theta 2 will equal all of this because this cancels. And of course 1 just disappears from there. 1.52. So the sine of theta 2 will equal, if you type this in your, now hopefully your calculator is in degree mode. It has to be in DEG mode, or maybe just D. So you'll have to look at your calculator to make sure. If you're in pre-calculus, you may be in radian mode, so you need to get out of that. So theta 2, to figure out what this is, we take the inverse sine of this. So it's like we have the answer, but what was the question? So that's when we use the inverse function. So inverse sine. Some calculators you type this, then this. Most calculators though, you type sine -1 of that. Work out to be 19.2 degrees. That makes sense because you're coming in from air. When you go into an optically denser medium, the angle between the normal and the ray gets smaller, and in fact it does. All right, so that's the end of part 1. I'll see you again for part 2.